Hi. Before starting new arguments, in order to recall previous video, let's provide some examples. Okay, example 1. Okay. Find the sum of from k equals to 1 to infinity logarithm 1 plus 1 over k. Okay, this is our problem. As solution, in order to solve this example, we need to use some properties of logarithm function. So I mean for any k for any k, the following holds: logarithm equals to logarithm k plus 1 over k, and equals to logarithm k plus 1 minus logarithm k. Okay, so this means that our series logarithm 1 plus 1 over k equals to for instance, for k equals to 1, logarithm 2 minus logarithm 1. This is the first term. Okay, plus logarithm 3 minus logarithm 2. This is the second term. Let's write the third term: logarithm 4 minus logarithm 3. And similarly, this is the third term, plus, and let's write logarithm, by the way, logarithm n plus 1, for instance, minus logarithm n, and this is the term in nth order, and so, well, this is a such kind series, and for such a series, the partial sum is a special sequence whose the general term are composed of the sum of the first n terms, namely S1 plus Sn. Okay, we found already this one, because we can say that S1 S1, S2, S3 and Sn, as you can see, the partial sum Sn, and here equals to, okay, you may see some terms disappear, and we have logarithm, let me write left hand side, Sn minus logarithm 1, which is already 0, and plus logarithm n plus 1. Okay. We need to find the limit of this sequence. Which is very simple, because we know already here 0, and limit and then logarithm n plus 1 and goes to infinity, so which is clearly infinity. So our partial sum is divergent, so Sn divergent means that our serial divergent. The sum is infinity. Okay. Let's write another example. Okay. Find the sum of sorry, here must be 3. Okay. Over k. Okay, we are going to find the sum of this series. The solution this is very similar to a geometric series, but is not a geometric series. If it was starting from 0 to infinity, then we call it a geometric series, obviously. But in this case, we can't say it is a geometric series, but the solution is very simple. So we may write 1 plus 3 over 4k equals to a geometric series, isn't it? Yes, we may write this one, and we are looking for this series. Yes, and we may calculate simply this geometric series, which is equal to, this is a geometric series which is convergent, because as you remember, a geometric series a power k, and if a, the element, the interval, open interval -1, 1, so this geometric series convergent. That's why, and the sum 1 over 1 minus a. That is why we may write here 1 over 1 minus 3 over 4. And so here is same. and we are looking for here and equals to, I think should be 4, and our answer is 3. Okay, this is a convergent series, and its sum is equal to 3. Okay, now we are starting to a new section. It's clear that to find a series, the sum of series is not simple every time. So that is the why we divide the topic of series into 3 subsections. I mean, in series, our main interest, and there are 3 types of series: a positive series, namely a series whose all terms are positive and alternate, and a power series. Okay, we are going to learn this kind of series separately, and our first subsection, a positive series. Okay, let's define it. Indeed, it's clear, but still we can make it clear. So let AK greater than or equals 0 for all natural numbers. Then we call this series positive. Okay. Immediately an example. Okay. For instance, you know already this series 1 over k, a series whose general term is 1 over k equals to 1 plus 1 over 2 and so on. Okay, it's clear that greater than 0, all terms greater than 0. This is a positive, okay, series. Let's write here examples. Okay, and another 1 to infinity and is clearly is not a positive series, and because -1 and a plus 1 over 2 and over 3 and a plus 1 over 4 and -1 power n over n, and so. Okay, and it's clear that this is not a positive series because one term is negative and one term is positive, so its terms, the signs of the terms successively change, and we are going to call this kind of series alternate series, but not now. Okay, by the way, we are going to provide some tests to understand if a series is convergent or divergent. So the first one of those tests is the comparison tests. Let's write here. And theorem 1. Okay, comparison test. Let AK and BK and be positive series such that AK smaller than or equal, and let's write here a constant C, and C BK, where C is a non-zero constant. Then, of course, this inequality holds for all natural numbers. Okay, then if AK is divergent, then BK so is BK, and if BK is convergent, so is AK. Okay. To make clear, let's use some geometry. Okay. Okay, this one BK and this one AK. So we may view EK is a small part and BK as a bigger part. So the comparison test says us if the big part is convergent, then the small part is already convergent. If if the small part is divergent, then the big part is already divergent. So this test, this is the how to work of these tests. Let's provide some examples. Okay. First example. Okay, find. Well, we may write here. Okay. Observe. Observe. Observe the convergence. The convergence of the series. Okay, I'm in this one. For solution, okay, and we know very well this series is divergent. So, and we know comparison tests. So by using this known series and comparison test, we are going to solve the example. So for any k, and we may write k and smaller than k plus 1. Okay, and also this is clear, and we may write here k plus 1 smaller than or equals 2k. Okay, we may write here, and if we have this inequality, then we have already 1 over k, 1 over k plus 1, or 2. So, and let's see the comparison tests. For any k, this inequality must hold, and here ak, here c, and here bk. So we may work comparison tests. I mean, we know the small part. We know the small part is already infinity. Then bigger part is infinity. So this series is divergent. We find the solution by using comparison tests. Yes, you know, for any k we have this inequality, okay, and by using comparison test we find the solution. There is a wrong, let me write here, wrong approach. If you take k for any k plus 1, and yes, this is true. And if you have this inequality and you may write smaller than 1 over k, then you may want to work comparison tests, and you say that here is and here is infinity. So then here is you can't say anything, because in such case the comparison test doesn't work. Let me write here why. Okay, for this situation, here is the big part 1 over k, and here is the small part 1 over k plus 1. You know the big part is infinity, but it doesn't mean that the smaller is also infinity. The small part may be convergence, who knows. That is why for such an approach the comparison test doesn't work. And another theorem, or a kind of test, theorem 2, we call harmonic or P series. Okay, and we call from 1 to infinity 1 over k and the power p a harmonic series, and this is convergent if p greater than 1, and divergent if p smaller than or equals to 1. Okay, examples. We wrote here already examples, so, and we may write here example 2, and yes, that we already know equals to infinity. And you may solve this example also by using the harmonic series or P series tests. Yes, this is infinity because P here, yes, P equals to 1. Another example. One over square root k equals to infinity because the P equals to 1 over 2. And another example. One over square root k2 minus 3. So let's observe the convergence or the series. So we know the convergence of the series. Yes, k power 2 square root k power 2. This means 1 over k because our series are all positive. So the harmonic test doesn't work alone, and also we have to use the comparison tests. We are going to use two tests, comparison tests and the harmonic series. Okay, for any k, square root k2 smaller, greater than minus 3. Okay, then if we have this inequality, then we may write here and yes, this one. So by using comparison test and the harmonic series, this one already infinity, and because we know very well this series. So if we have this one, then by using comparison test, this is the big part. If big part is infinity, then smaller part already infinity, then here must be infinity. Okay, another example. So let's observe the convergence of the series cosine power 2 k over k2. Yes, we observe the convergence of the series as similar to previous example. We use both comparison tests and the harmonic series test. Okay, for any k, we have this inequality. Okay, then if we have this one, we may write here over k2, and this one is a general term of a harmonic series, and p equals to 1. P equals to 3. So this means that the big part is convergent. So if big part is convergent, namely we write here smaller than infinity. If big part is convergent, then the smaller part is already convergent. Then we may write here convergent. Okay. Okay, next we have another theorem which we call limit test. Okay. Let AK be a positive series and limit k goes to infinity, k alpha multiply AK equals to L. Then if this limit greater than 0 and small infinity and gamma greater than 1, then AK is convergent. If L is greater than 0 and alpha smaller than equals 1, then AK is divergent. Okay, one example. Observe the convergence of K. Okay, let's use the limit tests for the solution. Yes, we may write AK plus 2, then limit k goes to infinity, k alpha AK. So let's choose alpha equals to 2 and k over 5 times k 3 plus 2 and equals to, okay, we are going to calculate this simple limit, which is 1 over 5. Then we may work the limit test because we choose alpha equals to 2 and greater than equals 0 and smaller than infinity, and the limit that we found, I mean L 1/5 greater than 0, okay, sorry, let me correct here. Here is L 1/5 and here is alpha equals to 2 greater than 1. So these conditions satisfies limit tests the first item, I mean this one. So then limit test works and says us the given series is convergent.